happens is that this point that you had collapses either to 0 or to 1. So this qubit gets destroyed in the process of measurement and becomes one of these poles, becomes either 0 or 1. Now, how does it happen? This is a probabilistic process, basically. There is a probability that it will become 0 and a probability that it will become 1. Now you see that the more this thing is close to one of the two poles, the more it's likely that it will end up being there. So, for instance, this thing is way closer to 0 than to 1. So when we measure it, like probably 85% of the times, a qubit is the main computation unit of quantum computing. So probably you know what a bit is. A bit is something that is either 0 or 1. A qubit instead can be any point on that sphere, which is called the block sphere. So you can see that it's not just like two things, it's a continuum of things, an entire surfaces of possible states. Now the most important thing is this here. This is also true vice versa. Obviously, so if I have like something like this thing here and I measure it along this axis, it's the same. I'm basically destroying the information and going up or down with equal probability. Okay, so this is the basis of something called conjugate coding, which is what we're doing there.
I am about to do that, yes.
Yeah, so we have a little helper which is basically formatting an Ethereum transaction right now, and as you know in blockchain, what you do is you sign the transaction. Signing the transaction literally means signing the hash of the transaction.
Such as that?
Exactly.
Which I've taken from Etherscan.
Yeah.
That thing there?
Do not take this one because if you can go to transaction helper.
I cannot run it.
No, I know, just show the code.
Oh, okay.
So, transaction util, transaction preparer, yes. If you, perfect.
Alright.
So in here, basically, what you have is, you see, we have from address as a sender, to address, we are sending to the 0 address, the value, which in this case is 1 ether, and then we are basically formatting this transaction. Now, Stefano cannot run this thing because Ether's RS doesn't build on this system, unfortunately, but what this thing spits out is the transaction hash that needs to be signed. Now, I will basically give this hash to him so that he can pass it to the TE, which has a secret key burned into it, and then we will get the signature out from the TE. Give me a second. I'm literally passing this thing on WhatsApp.
WhatsApp?
Yes. It's there, artisanal.
Can you send it on Telegram by any chance?
Yes.
Yeah, Telegram is. I think Telegram works better.
Okay. So I'm copying the hash. And I'm pasting it. So okay, I paste the hash on Telegram. It's that one. Just copy. Perfect.
Okay, so I'm gonna keep it here for safekeeping
Yes.
purposes. All right. So these are the two windows that I will use to pass. Maybe a brief. Can I have a minute to say what's in the box?
I also passing you the raw transaction, which is not signed. So if you put this on Etherscan, it will show you that it's a transaction, it's valid, but it's not signed. There is no signature, so it cannot be executed.
Why not?
Because it has no signature, right? So if you go on Etherscan and raw transaction signer. Wait, I'll send you the.
Nah, it's fine. I'm sure I can find it. This one?
Transaction, broadcast, maybe.
This one?
Broadcast for transaction. Yes.
Excellent.
If you copy paste that string and you, or was it this?
No, this is signed transaction.
Wait a second.
I just start by getting the sign convention first. And then again.
Yes, okay.
Yeah. All right. So, couple of things. Just for you to know what's effectively in the box. And
I have the thing, by the way. This is one.
you have the what?
Yeah.
Okay. That's a very interesting package.
Yeah, so if you copy paste that thing, the row transaction X, and you decode,
yeah,
you can see that there is no why is it? Yeah, okay, there shouldn't be a signature there. I think that's randomly calculated. Sorry.
It's okay. I will just do other things in the meantime. There's plenty of things to do anyway. So here is the very brief explanation of what's going on here. So that's all we needed for this demonstration. That's the packaged contents of this box as they were in London just before I put them in the hands of some trusted couriers that brought it here safely. It turns out, quite incredibly. I didn't imagine that. That's almost all we needed. What we really needed for this particular project was a skilled watchmaker who spent about a month of time going from theoretical quantum information person doing quantum gravity for his PhD to learning how to do experimental quantum photonics, because apparently that's what his job is right now. So that's the necessary components for this experiment, including personnel. He taught me how to do it yesterday, but I wouldn't have been able to do it without instructions, honestly. These are individual pieces. There's a photon pair source, which is a big laser. In fact, it's a small laser, but it has a big pump laser, and then there's a lot of loss. And a few photons, very sparse number of photons, come out of two fiber optic cables from the front. In fact, they are so few that we have to tape the box down and tape it at the bottom, because just the sunlight that comes through that little aperture in the front is enough to drown the signal from that and make it hard for me to run the experiment. The noise threshold goes high. So that's the generator of the photons that get into the experiment. And then there's the end of the photons. That's where the photons start their. So here the photons start their life. Here a brief few nanoseconds after, in fact I think picoseconds after, the photons end their life. They slammed against the detectors, and the detectors emit some signal which we can record on some microcontrollers and use to determine whether we have seen the 0 outcome, the 1 outcome, or we just missed the photo. And for your information, that's what the signals look like on an oscilloscope in our London office. These are just two of the photons, so the two photons that come out, and they come out. Typically, they should come out perfectly aligned of the laser, but because there's always photons drifting around, no matter how well we take that, there's a bunch of other signals. It's just that they are not perfectly aligned. They have to be timed exactly for the detector to look at it. Except the timing difference between them, you can't really see it here, but I can tell you the spacing is in the order of a few hundred nanoseconds between different pulses. The spacing between the photons is tens of nanoseconds, sometimes single nanoseconds. And so you need to have something which has that precision to detect which ones are actually the coincident, the correlated pairs coming from the laser, which is the signal for the protocol, and which ones are just random photons that come from the air and enter the box, and you don't want them because they carry who knows what information. And what you need to do is you implement a small piece of electronic circuitry, which is called a coincidence detection. And what it does is when the signals are sufficiently aligned, there's a bunch of MOSFETs and resistors that implement effectively an AND gate, but a very short-term one. And they translate these very short peaks, which by the way would be too short for the microcontroller to reliably detect anyway. And they translate them into a pulse that is longer, but only comes if they are sufficiently well timed. If they differ by even like 20 nanoseconds, the pulse doesn't come. It just gets lower very quickly. And so this allows us in hardware to detect coincidences before we pass them to the microcontroller. So one of the photons that comes out of the laser is entirely wasted. It's only used for this timing purpose. And it tells you when to expect something in the other detector. What is noise and what is not noise. Without that photon, you do not know which photons are the interesting ones and which photons are just random from the air. In fact, there's many more random photons from the air than interesting ones, and this is a cryptographic impact, because it allows you to hide some of the error. Even if you have a bit of error in your protocol, as long as there's enough thermal photons from the air, from the light, then those will drown whatever imperfections in your signal. You know, because you can do the coincidence detection, which ones are the right ones, but without the herald photon, you can't do it. Other pieces, practical pieces that the photons go through, there's a beam splitter. The beam splitter is a way to take a photon coming from one path. So you use effectively, we decided to use an encoding of qubits, which is called path encoding. We use the 2 fiber optic cables for each photon, and depending on whether the photon is in the first cable or in the second cable, the bit encoded is 0 or 1. And this is very classical, it's just classical light. But because the photons are quantum, what you can do is you can pass them through a reflective cube, which there's like a laser, a test laser coming through. This one is invisible. And in this cube, photons enter through one port and they get split on both paths at the same time with a phase in between. So now the photon classically is on both paths in superposition, and the phase between the paths is the thing that encodes the bit. So if you try to measure the 2 fiber optics, you plug them into the detector without doing the correct measurement, you just get 50-50 random coin flips. Nothing interesting. If you want to decode them, you pass them through a second one of these, which scrambles them and makes them come out of the correct port again. So this is a way to pick the basis that you want to encode information into and decode information from. Then you have some switches, which are used to communicate classical choices to the photons. It is very hard. I mean, photons travel really fast, speed of light, which is fast. You cannot really time operations mechanically that fast. Nothing complicated. So the best way to work with photons and implement quantum computations is to have fixed sets of equipment that do different things and have one kind of component that is fast, which is a switch. And all the switch does is decide path 1, path 2, nothing else. And you have a bunch of these switches together, and you can use one to decide which basis, one to decide which bit to encode, then they go through 4 different paths, then they get merged together, and they get sent to the destination. The destination does the same thing. It has 2 switches that decide which basis to measure in, they go through 2 different paths, merge again, and get detected. And so you have all of these paths that are alternatives. The photon is only in one of them, or in 2 of them in superposition, or in many of them in superposition, but they need to be merged back into one, and that's what fiber mergers are for. We only need 2-to-1 fiber mergers. So 2 fibers come in, it's fused fiber optic, it's a very precise process. The photons come into this junction, and they come out of a single fiber. And this is a polarization, all of this is polarization maintaining, because we use polarization for part of the process. And finally, we have the stars of the show, which are microcontrollers. There are 2 of them. One of them controls the encoding side of things, one of them controls the decoding side of things. In reality, they would be in different places.
Alice in Wonderland.
Alice in Wonderland. But in here, because we need to do a compact demonstration, they're in the same box. One of them decides which basis to encode the secret information into and which bit to encode, and the other one decides which basis to measure the information from. And so they are attached to the various switches that we have that control the paths of the photons. That's the way this experiment runs. Laser is on, box is sealed, hopefully there's not a lot of interference in there right now. So I'm going to start running next.
So if you go on Telegram, you can see I sent you the right RPC at the moment.
Okie dokie.
Okay.
I will control them. Yep.
So you can see it's considerably shorter because it's actually not signed.
Yep. So this is the one.
Yes.
And I'm going to
If you place it there, yes.
Yep.
The code, you will see that there is basically no signature information. It should come right after value. It does not because there isn't.
It does say valid false.
Yes, because it's not signed. Cool. So I also asked you the hash, and then you can go
Yeah, so first things first, there is a bit of the protocol that involves the secret that these two enclaves should have. The information in this secret is a couple of tables of bits that need to be produced. There's 2 rows in this table, and we need to pick the ordering of the bits in the table, so whether 0 means X or 0 means Z. This is the secret information that's shared by the 2 TEs. We put it as the first input of our program, so let me flash the 2 chips and run the programs. So first things first, I'm gonna flash. Program 1 goes on COM4. That's the one, it's waiting for the hex string from the serialization utility. Program 2 goes on COM6. I had to write them on my arm, remember? And that's also waiting for the same information. So this is the secret table that the 2 TEs would have stored inside and would use to decide how to encode the data and how to decode the data. So this information comes from a small utility that we have, that Fabrizio has written. I shall not take credit for this. I'm going to just put 2 security bytes because it's a short demonstration. So let's say 0x0123, 0x4567, and 0x89AB. And this gives me, this states there are 16 bits here, 16 bits here, 16 bits here. There's 48 bits. They get encrypted using the TE key. So technically you'd give this information can't be read from the outside, it's decrypted by the enclave. So you can pass this, but only the enclave knows what the table is. So this is encrypted with a key that's secret to the enclave. Use it as you see fit, and I shall see fit to use it here. So enter it on the controller, on the sending party, so Alice, enter it on the receiving party, say Bob, and now I am told, okay, this is valid information, please provide the input to your program. The input to my program is going to be the hash to sign?
No, one, if you go on Telegram, this is the rule transaction. Yes, that one.
This one?
7cc.
7cc.
Yeah.
And so this is the hash of the transaction, which I will put here. And if everything goes well, which it never does. Well, no, not error. The watchdog has killed the program. Let's try again. These things are as fiddly as they can possibly be. This time I will be fast. Done.
Yeah.
Bunch of bits were generated. For debugging purposes, I have printed them. You wouldn't. This is the secret information. See, the information I sent initially as, let me just kill them so that the watchdog doesn't restart them. The information that I sent, this was secret information that was decoded by the TE internally, and it contained these secret basis choices, these secret bits for the Z basis, these secret bits for the X basis. And these were used to generate a bunch of switch inputs that determined whether the photons went into the X path or the Z path, that whether the bit encoded was the 0 bit or the 1 bit. And on the other side, the detector received these photons, looked at the detectors, got some bits out of the detection process, and these were the bits that were obtained. Sorry, these were the bits that were obtained. These would be the measurement outcomes. They were validated, they were valid, and the security was verified. This was a fairly clear, fairly well-tuned procedure, and it worked out for this program execution. So now the TE internally has a key. The key was used to sign this transaction, and now this information that I have should be the one that I paste, right?
Yes.
If I've done everything right, which I am not sure I've done, how do I verify it?
Yeah, let's see. I think you should give it to me so that I can give you the RPC, because that's just the signature.
Yeah, but can I not verify the signature by No? Enter scientist?
I don't know if it tried. I don't know if the format is.
No, fair enough. So I'll just send it to you.
Just send me the transaction. Now, what I would like to show you my screen, but it's a nightmare with two computers at the same time. Yes, so. Second. Now, basically, I will copy this signature into my program.
You have the cable?
No, it's.
I mean, I'm not.
No, the problem is not the cable, or is my computer. Okay. Card run release. Okay, now I should have this thing, which is posted here. Okay, now if you go with this one,
I do what?
just copy it in the transaction decoder.
Yeah. This one?
Yeah.
Yeah. And I
Now
decode it.
in the code, you will see it's all the same, but now there are 3 more parameters, D, R, S. Those are the signature parameters. So now the transaction is signed, and indeed it says valid true, because the transaction now can be executed. So,
yes.
and the important thing is that all the signing happened on the TE. So, you know, in the real case scenario, only Alice has the private key, sends it to the TE, and Bob basically gives the transaction. It works like another wallet, basically. Bob takes the transaction, feeds it to the TE, and the TE signs it for him, and then he broadcasts it. With the difference that he can sign any transaction he wants with that secret key only once. Then he cannot do it anymore because it destroyed the quantum information encoding the table in the process. And that's it.
Yeah. Thank you. Thank you very much.